Introduction to Neural Networks. Please welcome Mike Craig.
Hello. How's it going? Cool. So as you said, I'm Mike Craig. I'm a data scientist at Warby Parker here in New York. And this is Introduction to Neural Networks with TensorFlow. So I wanted to kind of split my talk half between introducing like the concepts behind neural networks and how they work, and then diving into the code so you can actually like use this stuff. But I didn't want to make any assumptions about what people know. So I'm going to have like a really just kind of a high level overview of like machine learning and then the problem, but really with a focus on how to set up these problems operationally. So what is machine learning? Machine learning is a subfield of artificial intelligence that deals with pattern recognition and predictions and forecastings and things like that. It's much more statistical than traditional artificial intelligence algorithms. I mean, when you think about like Minimax or A-star, these are kind of like heuristical algorithms to kind of pick like an optimal action, whereas machine learning is a little more fuzzy. It's a little more like statistical and using data to kind of get at an approximation of what the optimal solution could be. And so that's kind of one way to think about it really is that all the machine learning is just kind of like function approximation. And so basically any function that is computable and where the form isn't really that obvious, machine learning can be a good candidate. So here's a couple examples, like handwriting recognition. So I mean, humans could look at that and I could 504192, but how do you tell the computer to encode these? Like for example, this one right here is slightly tilted, whereas this one is not as much, and all these like very fuzzy differences cause you're gonna have this crazy rule set if you wanted to try to program it normally. Facial recognition is another thing. So if you let's say you had a facial recognition app on your phone and you've also like never taken a US history course or something, you could you could put that image through the facial recognition, and it would like use machine learning to kind of find the face in the image and like find all the different key interesting points about that face, and then like look it up in a database and everything, and it'll tell you that it's George Washington and that you're an idiot for not knowing that. Speech recognition, so like Siri, Google Now, Amazon Echo, right? Taking like audio signals and turning them into human words is something that takes a lot of machine learning. Also, I guess the other half of that too, like taking natural language processing and taking words as we speak them and like turn them into something that's like more structured and useful for a computer to understand. And the last example, so knowledge discovery. So this is something that maybe it made the rounds on the internet 6 months ago. Maybe you've seen it, but somebody created this neural net that you give two images and it kind of learns the artistic style of the images and can kind of like combine them and draw the image in the style of that other image. And they use like convolutional neural networks to do this, which we're 100% not going to get into in this 25-minute talk, but just some kind of examples of what you can do with this stuff. So really high level, I'm gonna get a more formalized definition of the machine learning problem. So there are two main types of machine learning: supervised and unsupervised. And we're going to deal with supervised, and that's basically you collect data. You have an input data that kind of describes all the information for a particular data point that you're observing, and then what the observed label for that is. So, for example, handwriting recognition, you could have the input would be the pixels in the image, and then the output would be like it was a 1, it was a 2. And versus unsupervised learning, which is you only have inputs, and you're kind of just saying, okay, give me the objective is to find patterns, and like give me this like what kind of clusters do you see, what kind of like hierarchies do you see in the data. But we're gonna deal with supervised learning in this talk. So a little bit more formally, like this is basically how you want to structure your supervised learning problem. You want to collect these input and these output matrices like this, where each row is like an observation of something that you see, and then each column is just like the different variables, the different pieces of information about that point. So. Like I said, for handwriting recognition, one row could be an image, and then it's just like sort of flattened out, and then each column is like all the different pixels in the image. And similarly, your output is also a matrix. Typically, like in many cases, they're just kind of one column, but you can have more than one column in your output, and so for example, let's see. Yeah. So, for example, with handwriting recognition, what you would have is you might have 10 columns of outputs that are all binary, whether like 0, 1, whether that particular image was a 2 or that particular image was a 3, and so on and so forth. And so that's kind of how you want to. This is like the prerequisite before you even throw any algorithm at this. You want to be able to collect this type of data about your problem. So this, too big. Let's get into neural networks then. Okay, so this is what a neural network looks like. You basically have all these input nodes, and they sort of propagate through the network to produce these outputs. And the inputs as are defined by that like X matrix, right? And so that gets fed in and goes through the network through these like arrows, these connection weights, these arrows to the next layer of units, and then those units are activated in a certain way, and then they move on to the next layer, and so on and so forth. And so some of the terminology for this. I think I said it already, right? So neurons are activated at some level, which is then propagated forward through the different layers. And then the strength of this activation is controlled by these arrows, these connection weights, which is going to be what we're going to try to train during this process. And so, in fact, you can kind of see that the weights between each layers can be described as a matrix. In between, so there would be like a weight matrix here, and there'd be a weight matrix here, and these are the matrices that we're trying to like optimize to have the network learn something useful. So, and then one other thing is that after the connection weights and the inputs are fed forward into the next layer, the unit is passed through what's called an activation function, which I'll describe in a second. But I'll describe in a second. So more formally, this is how the neuron's computation is. So if I have some unit z, and it's going to be a function of the previous layer's inputs multiplied by this weight, and then passed through this activation function, and then this would then be the input into the next layers, and so on and so forth. So what are these activation functions? Well, basically, activation function allows you to kind of create this like nonlinear relationship between, or it allows you like to define these nonlinear relationships between your input and your output. If we didn't have an activation function, just by looking at this equation right here, it would just be like without that f right there, and it would just say that each unit in the layer is just a function of the inputs multiplied by some weight, and so if that's the case here, then this would be a function of this input multiplied by this weight. So this is a linear function of a linear function, which is a linear function. So there would actually be no point in having this like middle layer at all if we didn't have this activation function. So that being said, you could have a linear activation function if you wanted, but that totally defeats the purpose. I mean, sometimes you can put a linear activation function at the last layer, at the output layer. But again, you would lose that nonlinear relationship there. Another choice for an activation function is a sigmoid, Kind of looks like this. So they're known as like squashing functions because they take the entire domain from negative infinity to infinity and kind of squash it onto this 0 to 1 range here. And this is used a lot because it can kind of like very hand wavy be interpreted as probabilities. And so you might want to like just throw a sigmoid activation function at the end of the output layer, and then if you were classifying something and it came out with an output of like 0.7, you could sort of say, you can kind of say that, yeah, we're like the network is 70% sure that this is the case. Another choice is a hyperbolic tangent, which is, as you can see, it kind of looks similar to sigmoid. Maybe it's a little bit steeper, but it goes from -1 to 1 rather than 0 to 1. And this is kind of sometimes preferred in like some of the hidden layers because it's symmetric around 0. And so with the sigmoid, there's like this inherent bias where, I mean, it's symmetric around 0.5, right? And a lot of the math just works out better if you make the assumption that a lot of these are just like normally distributed and symmetric around symmetric around 0. Another choice that is popular nowadays is the rectified linear unit. It looks like a linear unit from 0 on, and then there's like that nonlinearity at 0, and it's just basically it's literally defined as the max of 0 and x. And this allows for like a lot of the expressive power that you get from a linear unit. I mean, we're not squashing anything, and it can go up to infinity here, but it also has this nonlinearity allows it to not just be like a linear function. Also, it has the nice property that it actually is 0 for any activations less than 0, right? So you can kind of think of it as it's a way of like turning off a neuron, and there like yeah. So you can have some neurons that maybe just aren't it receives some input and it's deemed not that useful, and it's kind of just like turned off, so to speak. So how do you train these neural networks? Well, basically what you want to do is you want to define some loss function, and this is a function that's basically saying like how bad is the network right now, and you collect this prediction. This is what we'll call y hat. This is what the network predicts for a given point, and then you have your observed variable, and then you basically just define some kind of loss function. Here is just mean squared error. It's just the mean of all the squared errors of all of the between all the observed and the predicted. But there are other possibilities too that you could use. And then the idea is you run these like gradient descent approaches, which I'm not going to get into the math behind it. Also because you don't need to know it, because that's one of the benefits of TensorFlow. But the basic idea is that you update the weights according to their contribution to the error. And so you're sort of like descending down this error curve by picking better and better weights as time goes on. And there's just so much literature about like how to optimize and how to and all these different algorithms and all these different optimizers that you could use. But that's the basic idea for a lot of these. Let's get into code. That's just a bunch of imports. Okay, so we're gonna run through an example using that handwriting analysis, or handwriting recognition data set that I described before. So I'm gonna load in data from scikit-learn because it's in there, and so here I am just loading it in, and then I am the only thing I'm going to do to change it is I'm going to use pandas, and I'm going to get the dummy variables out of here. So instead of beforehand, it was just like the y variable is just a list of integers from 0 to 9, and I'm saying I want to transform that into a matrix with 10 columns that's just binary, and it's 1 if that's the case. So if this particular sample is 3, then the third index would be 1, and everything else would be 0. That's all I'm doing there. And so yeah, let's run this. So as you can see, there's about 1,800 samples, 64 columns, so there's about 64 pixels in each of the images. And like I said, this output matrix is like the 1,800 by 10. And here are some samples of what they look like. So very, very low res, but yeah, you can kind of see that they're just grayscaled, and each pixel has a value that's 0 to 255. That's describes the intensity at that spot. So let's get into TensorFlow. So TensorFlow is an open source library by Google that to build a lot of these models. And one of the really cool things about it is that it's kind of like Theano, if you've ever played with that. It's like symbolic, so you can just tell it the equations rather than like actually computing the thing on the data. You just tell it what equations you expect, and then it'll then say run off this data, and it'll plug it in and run this. And that's really useful for computing gradients, like we were talking about before, to training these networks. We don't even have to worry about that. We just have to worry about how to specify the network and then say update it. Oh, sorry. So this is yelling at me because I already have a session open. But you create a session in TensorFlow, and then that's what you run all of these operations on. And basically, yeah, so a session creates this computation graph that describes all of these operations, and then you can kind of just say run it. So let's get into some of this. So in TensorFlow, you want to define all of your inputs as variables here. And so I'm defining the input and the output as placeholder variables. And I happen to know the shape ahead of time, right? So I know the shape of the data is 64 dimensions, right, for the input, 10 for the output. And then I put none here because that's basically just saying I don't care how many samples I have. So like later down the road, if I want to plug in a subset of this data set, that's fine. Obviously the number of like dimensions needs to be fixed, but that's what that none means. It allows you for like batching and things like that if you want to do that. Here is the network right here. We're just going to define the computation for the network. This is actually a network with no hidden layers. We'll add the hidden layer in a second, but basically we define this weight matrix, and this is the weight matrix going from the input to the next layer, which in our case is the output, so we know the size of that. And then there's also a bias unit, so if you think of like, you know, a linear regression, like y equals mx plus b, this is the b. And that's usually, you know, needed in a lot of these, right? And then here's the equation for the network. So we're doing a matrix multiply on the input and the weight matrix, adding in the bias, and then passing that all through a softmax function, which I haven't described softmax, but it's just it's another type of activation function that basically allows you to see probabilities across many different choices. And so this is actually, since there's no hidden layer, this is actually pretty much equivalent to like logistic regression, if you're familiar with that, or softmax regression, I guess technically, because it's really the hidden layer on the neural network that actually makes it neural networky. So what we're doing here is we're just setting this variable y hat to be the output of these inputs. And notice we have not given it any data yet at all. We're just describing how it would work. Then we define our loss function. I'm just going to use mean squared error loss. So just the square of the difference between y hat, which is our prediction out of the network, and y underscore, which is this placeholder that I'm using for the actual output. Just square it, and then just take the mean of that. I'm also going to define some functions here if I want to know like how well the network is doing. So this is just computing the accuracy. So we're taking the argmax. So since it's softmax, basically, since the output's going to be like 10 numbers for each sample, I just want to pick the one that has the highest probability. So I'm passing that through argmax here, and we're basically saying, is my predicted choice equal to the actual observed choice? And then taking the mean of that would give us the accuracy. Then at the very end here, I am saying, I'm saying, okay, let's take let's pick an optimizer to use. So I'm using this Atom optimizer. There's a gradient descent optimizer. There's an eta grad. These are just like different algorithms, different optimization algorithms, and you give it a learning rate. So this is basically like how steep you want to descend down this curve. So because a lot of these error curves are not like just smooth at all; they're pretty bumpy, and so you can overshoot if you have a really high learning rate. And so or it'll take forever to train if you have a really low learning rate. So this is a parameter that is something that the program has to take into account. And we're just saying, okay, give us this optimizer with these parameters and just minimize this error. And so this error is a function of this y hat, which here's the equation for that, right? And so it kind of follows it backwards, and it can update, and it basically it updates the weights such that it minimizes this error. And at the very end, I'm just saying initialize all these variables. I'm saying session.run initialize the variable. So like I said, you run all these things on the session, and I'm just telling you to initialize it all. Okay, and now let's actually get into training it. So I'm going to run I'm just going to go through 1,500 of these training iterations, and I'm just going to say this is what I defined up here, right? This optimizer, and I'm just going to say run, and I'm going to feed it. You have to feed it. You have to tell it what data it expects, right? So remember, so. Basically any of these variables you could pass in as something, right? Or any of these placeholders you can pass in as something. And so here I'm saying, okay, for every time you see X, actually give it the actual data we're talking about. Every time you see Y, give it the actual data we're talking about. And then I'm just going to print every 100 iterations. I'm just going to print the accuracy. So we're doing okay, I guess. 77% accuracy is not bad, I guess, but if you hired someone who couldn't recognize handwriting 77 or 33% of the time, what are you doing with your life? So let's add a hidden layer to this. And the way the way you do that basically is we're just going to create 2 weight matrices now and 2 bias units, and then define the equation in 2 steps, basically. You can name them whatever you want. I'm being extremely explicit right now and verbose, but here's the weight matrix going from the input to the hidden units. I'm now initializing it to some. Before I was initializing it to 0. Now I'm initializing it to these random variables. But other than that, there's nothing too crazy here. And then here's the weight matrices from the hidden to the output. Same with the biases. And then here is I'm defining the activation through up to the hidden unit. So this is multiplying the input by that first weight matrix, adding the bias, passing it through a sigmoid activation function. Then I'm just taking that, multiplying it by the second weight matrix, adding in that bias, and passing through a softmax activation function. The rest of this code is the same. I do have to redefine it with all these new changes, but the rest of the code is the same, and now we have a hidden layer that is doing better. It's a little bit slower to train a lot of the times, just because there's a lot more parameters to train on, but 95% accuracy is much better. I mean, we could definitely improve that even further, but that's good enough, I think, to start. So I want to give a sense of an intuition behind the hidden layers of these neural networks. So here's a toy data set from scikit-learn. It's basically just an inner circle surrounded by this outer circle, and then the inner circle is its own class, and the outer circle is its own class. And the task is to be able to approximate this function to be able to separate the two. So a human looking at that would be, okay, just put a circle in between that, and then you're good. We'll see if the neural network could do that. Basically, I just took all this code and turned it into a couple of functions here, but it does most of the same thing, and then I added some code to plot as it trains. So this is no hidden layers. It's having a real tough time. It's so no hidden layers. Remember, is basically it's trying to find a linear function. So it's trying to find a line that could separate these. It's kind of like a mean thing to ask it, right? Because it's not going to be able to find it. Now, if we add in the hidden layer, it's actually able to find it. So the hidden layer actually allows it to kind of like find this kernel. In math terms, it's called a kernel, and it kind of just like finds the shape of this kernel, and it's able to eventually learn that. So starting to run out of time, but really quickly, here's some other features of TensorFlow. They have GPU computing built in right out of the box. You don't really have to. You just have to specify. You have to set it up, but you don't really have to specify anything else. You don't have to change anything else in your code. Also, cluster computing they released pretty soon or pretty recently. I personally haven't messed around with it, but it's again, you don't even have to think about it. It figures out how to parallelize all these operations, and you just have to obviously set up the cluster and everything. And then this notebook is on my GitHub. My username is mcraig2. I don't know who took mcraig, but and then my in the PyGotham talk repo, I have my code. Are there any questions?
Do you have,
oh, yes.
Do you have a rule of thumb about how to set up your middle layer, about how many neurons you will start with, or is there a lot of trial and error for that?
Sure, it is a lot of trial and error, and it does depend project to project. So basically, one way to think about these hidden layers is like if your hidden layer is smaller than your input layer, then you're basically asking the network to reduce in dimensionality your input. And if it's so if your problem is set up in such a way that you think that that's like that it's okay to do, is like you're not worried about it being that lossy, then that's fine. Usually, when I'm trying these out, there's definitely no one number, but I try to go anywhere between like 2/3 of the number of input dimensions to 2 times, and then just kind of see performance-wise like how it works. I mean, you can also add in many hidden layers too. I mean, all this stuff, but I usually try to start pretty simple, one hidden layer, and then yeah.
So do you have experience with other deep learning frameworks? And if so, can you speak to the performance differences?
Yeah, so TensorFlow did come under fire pretty at the beginning because it was not as performant as some of the other ones. But I think it's better now. I have messed around, I've messed around with Theano, and it's pretty performant. I've messed around with Cafe and some other ones, and I just personally prefer the interface for this. I'm also like I'm not running ginormous networks, so I'm not too concerned about performance, but it's definitely like TensorFlow is definitely fast now, if that makes sense, compared to the other ones.
Have you seen, just following up on that first question, have you seen any examples of using gradient descent on the parameters? So like how you're saying, training the different network sizes, like, because I've been having trouble finding like specifically gradient descent on the parameters and then training that off of the network so that you don't have to self-tune.
Gradient descent on like how many?
Yeah. Have you seen any
units?
examples of that with TensorFlow?
So
I've seen it in Theano.
this that's the whole field called like hyperparameter optimization. And
Yeah.
things. Yeah, I mean, I haven't personally used it. I think that there's a lot of like there are a couple other ways you can do that. I mean, there's like a grid search type of approach where you just try a bunch and then pick the one that has the best. There's like just a random search actually turns out to be pretty better, even better sometimes than grid search. But running gradient descent on those hyperparameters, I don't personally have experience with, but it could be something interesting. I don't know. Yeah. Anyone else? Cool. Thank you. Turning them into human words is something that takes a lot of machine learning. Also, I guess the other half of that too, like taking natural language processing and taking words as we speak them and like turn them into something that's like more structured and useful for a computer to understand. And the last example, so knowledge discovery. So this is something that maybe it made the rounds on the internet 6 months ago. Maybe you've seen it, but somebody created this neural net that you give two images and it kind of learns the artistic style of the images and can kind of like combine them and draw the image in the style of that other image. And they use like convolutional neural networks to do this, which we're 100% not going to get into in this 25-minute talk, but just some kind of examples of what you can do with this stuff. So really high level, I'm going to get a more formalized definition of the machine learning problem. So there are two main types of machine learning, supervised and unsupervised, and we're going to deal with supervised, and that's basically you collect data. You have an input data that kind of describes all the information for a particular data point that you're observing, and then what the observed label for that is. So, for example, handwriting recognition, you could have the input would be the pixels in the image, and then the output would be like it was a 1, it was a 2. And versus unsupervised learning, which is you only have inputs, and you're kind of just saying, okay, give me. The objective is to find patterns, and like give me this like. What kind of clusters do you see? What kind of like hierarchies do you see in the data? But we're gonna deal with supervised learning in this talk. So a little bit more formally, like this is basically how you want to structure your supervised learning problem. You want to collect these input and these output matrices like this. A computer to encode these. Like for example, this 1 right here is slightly tilted, whereas this one is not as much, and all these like very fuzzy differences cause you're gonna have this crazy rule set if you wanted to try to program it normally. Facial recognition's another thing. So if you let's say you had a facial recognition app on your phone, and you've also like never taken a U.S. history course or something, you could. You could put that image through the facial recognition, and it would like use machine learning to kind of find the face in the image and like find all the different key interesting points about that face, and then like look it up in a database and everything, and it'll tell you that it's George Washington and that you're an idiot for not knowing that. Speech recognition, so like Siri, Google Now, Amazon Echo, right? Taking like audio signals and predictions and forecastings and things like that. It's much more statistical than traditional artificial intelligence algorithms. I mean, when you think about like Minimax or A-star, these are kind of like heuristical algorithms to kind of pick like an optimal action, whereas machine learning is a little more fuzzy. It's a little more like statistical and using data to kind of get at an approximation of what the optimal solution could be. And so that's kind of one way to think about it really is that all the machine learning is just kind of like function approximation. And so basically any function that is computable and where the form isn't really that obvious, machine learning can be a good candidate. So here's a couple examples, like handwriting recognition. So I mean, humans could look at that and I could 504192, but how do you tell the
Introduction to Neural Networks. Please welcome Mike Craig.
Hello.
How's it going? Cool. So as you said, I'm Mike Craig. I'm a data scientist at Warby Parker here in New York. And this is Introduction to Neural Networks with TensorFlow. So I wanted to kind of split my talk half between introducing like the concepts behind neural networks and how they work, and then diving into the code so you can actually like use this stuff. but I didn't want to make any assumptions about what people know. So I'm going to have like a really just kind of a high level overview of like machine learning and then the problem, but really with a focus on how to set up these problems operationally. So what is machine learning? Machine learning is a subfield of artificial intelligence that deals with pattern recognition and